Illustrative Math, Algebra 2, Unit 4, Lesson 11 is called Evaluating Logarithmic Expressions. Goal today is I can use known values of logarithms to estimate the value of other logarithms, and I can use technology to determine the value of a logarithm. Okay, so a little warm up here. Evaluate mentally. So if there's no base written, we just go assume that it's a base of 10. So remember here, if I have log base b of x equals y, this is log form. To get to exponential form, it's b to the y equals x. Okay, so this is log form, and this is exponent or exponential form. Okay, so this would be equals what? That's what we want to know. So 10 to what power equals 10. Obviously, this is a 1 here, so this has to be 10 to the first. We want to know what this equals. So again, we assume it's a base of 10. 10 to what power equals 10,000. And obviously, this here would have to be a 4. So it would be 10 to the 4th. Gives me 10,000. Okay, over here, this is 10 to what power equals 0.1. 10 to what power equals 0.1. I'm going to write it as 1/10 because I think it's easier to see. And the answer there is going to obviously be -1. Negative powers will flip it. Okay, so 10 to the first would be 1 over 10 to the positive, or 10 to the negative first would be 1 over 10 to the positive first. And then the last one here, 10 to what power equals 1 over 1,000. This is going to, well, 10 to the third is 1,000. So 10 to the negative third would flip it and make it 1 over 1,000. So this one would be -3. Okay. I do want to add one thing here. If I gave you something like this, if I said log base 2 of 10, we want to know what that equals. So right now, the only way we can do it is if it's not, like 10 is not if you take 2 to a whole number powers, I can't get 10 because 2 cubed is 8. And 2 to the 4th is 16. So we know it's somewhere between 3 and 4. So right now, the only way that we have to do is to estimate this by trial and error. I'm going to show you a little shortcut here. This is actually called the change of base rule. So if I have log base b of a, we use a, I can change that into log base m of a over log base m of b. So basically, as long as these bases match up, you can use any log. Okay, so like this one here, if I wanted to, usually we use a base of 10. So if I just typed in log base 10 of 10, and we don't write the 10 there, over log base 10 of 2, and when it's base 10, we don't write the base. This now allows me to be able to type it into my calculator and get a much quicker number than just kind of like guessing and checking, plugging in numbers on 2 until I get close to 10. I can type it in and I'll do log base 10 of 10 divided by log base 10 of 2, and that'll give me 3.322, which I knew it was somewhere between 3 and 4. So here, if I tried it up here, 2 to the 3.322, let's see if I get close to 10, which I should. 2 to the 3.322. Sure enough, it's, yes, 10.0005. I'll round it to. All right. All right. So have you ever played the game of War with a deck of playing cards? So here's the directions here. If you have a partner and you want to write down all the logarithms on my next slide, you can. But the way we would do this if you were in a classroom is we'd have these all written down all these logarithms, like for example, like if this was a card here, if it looked like this, it would say like, log, whoops, it'd say like, log base 3 of 27. Okay, so we all know this is 3 to what power equals 27, which obviously that power would be 3. So this card is worth 3, okay? And then like, let's say you got another card here. Okay, your partner flips this card and it says like, log base 2 of 4. Well, 2 to what power equals 4? Well, that's 2. So this card has a value of 2. So this card here wins and this card loses. So you would take that card. If you had the log base 3 of 27, you would take the opponent's card. And you just keep going back and forth until somebody wins all the cards. Okay. Or you can, to make it shorter, you can play until you've gone through all of your cards and just count them up. But since we don't have like since we don't have like people to play with here on this video, I'm just going to go through all of the logarithms and just show what they are. Okay, so I did some of them to kind of speed it up. All right, log base 5 of 1/25, that's -3. Let's see here. This is going to be -3 as well. And why? Because 10 to what power equals, I'm going to write it like this, 1,000th instead of 0.001. Just because then I can see it a little better, because 10 to the third is 1,000. If I make it -3, there it is. This one's going to be 10. How do I know it's 10? Because 5 to what power equals 5 to the 10th? Well, obviously this would have to be a 10 to make these two equal. All right, this one here, I did that. Obviously these would have to be 1. This one here, this would be a little bit harder. So, 2 to what power equals 20? So you're going to have to kind of estimate that. It's probably going to be between 4 and 5, because 2 to the 4th is 16, 2 to the 5th is 32. But if you want to use the little trick that I showed you with the change of base, you can just change them to a base 10 and type in your calculator log of 20 divided by log of 2. That'll give you an even more accurate answer. Log of 20 divided by log of 2, and we get 4.32. All right. All right, so this one equals what? 10 to what power? Gives me 1/5. So this one, I can't take 10 to a power and get 1/5. So I'm going to have to type in to my calculator log of 1/5 base 10 over log base 10 of 10. And that'll give me a better answer than just guessing and checking. Log of 1/5 divided by log of 10. And I get -0.699. 2 to what power equals 2 to the 10th? Well, that's going to have to be a 10. So maybe you're seeing this on these rules here. Like if you look here, if these are the same, it equals that exponent right there. Same thing here. You see how these match up? It equals that exponent. So that's like a rule that you're starting to learn. Also, if the base and the number next to the logarithm are the same, it's always going to be 1, as long as there's no power there. Or you could kind of think of it like this. This is 10 to the first, right? So it kind of looks like this. So this equals that power. Okay. Let's see here. A couple more. I'm not going to go through and do all of these, just because I'm going to try to keep the video as short as possible. If you want to check any of these, you can type them all into your calculator. If you want to write them all down and do them, that's fine. Do a couple more. So this one, 5 to what power gives me 10? It's not 2. A lot of people say 2, but no, 5 squared is 25. So I would type into my calculator log base 10 of 10 over log base 10 of 5. And that gives me 1.43. Let's see here. I'll pick a couple more. These ones are going to have to change a base formula for these. Let's see here. Let's find one. Here's a good one. This one here. 2 to what power equals 1? 2 to what power equals 1? That's going to be 0. Right? Any base, any non-zero base to the 0 power is going to always equal 1. So that's another thing that you should see here. If this is 1 right here, it's going to be 0. So kind of like here, look at this one. 10 to what power equals 1? Well, it's got to be 0. Same thing here. 5 to what power equals 1? Well, that's got to be 0. Okay. So you're starting to see how this works here. If that's 1 next to the logarithm, it's always going to be 0. All right, here's that rule that we had before. We got these matching up, so the whole thing's going to equal 10. Okay, and again, you could write it out. This is my base 10. I want to know what it's equal to. 10 to what power equals 10 to the 10. And then you can see, oh, okay, it would have to be a 10 right there. But, once you learn the shortcut, it makes things a lot easier. And here's another one. This is kind of the same, kind of the same rule right there. Okay, these match up. Then it's just equal to that power. Here's a negative exponent. Here's just a really easy one. 5 to the third equals 125. So there's a bunch of them there for you to do. All right. To solve the equation 10 to the m equals 19, Tyler writes the equation in logarithmic form. So m equals log base 10 of 19. He then presses the log button on the calculator, enters number 19, and writes down an approximation of 1.279. Priya follows the same steps on her calculator and writes down 1.27875. Experiment with your calculator until you understand how to evaluate log base 10 of 19. What value do you see on your calculator? So I'm going to write it. I'm going to type it in here. Log. So I don't have to actually put the 10. If I just hit log without a base, your calculator assumes it's base 10. It's called a common logarithm. So I'm just going to hit log of 19. And sure enough, yeah, I get something similar. 1.278753601. So this number is going to go on forever because it's what we call an irrational number, and we can't. It's going to have to be rounded. Okay. The only way to write it exact is this. We could say log base 10 of 19. This is exact, but to actually understand what number that means, you have to kind of convert it to a decimal. Okay. So why might log base 10 of 19 be expressed different ways? I would say we have to round or leave it in log form to be exact. And we also have that exponential form too up here. This is exponential form. This is your log form. Okay. The exponential form is a little different because your variable's in the exponent. This one here is solved for the exponent. So they all do different things. Okay. Express the solution to each equation using a logarithm. Okay, so this would be log base 10 of 24 equals m. So you could write it like that, or if you don't want to put the 10, we know that log of 24 has a base of 10. So this is exact. So I'm just going to leave it. I'm not even going to type it into my calculator or anything. I could get a decimal, but it'll be rounded. So I'm just I'd rather just leave it. It's easier. So same thing here, log base 10, I won't write the 10, of 750 equals the exponent. So So there you go. This is exact. So I just leave it. All right. So, oh, it does say next, find the approximate value on a calculator. So I guess I can do that here. I just type in log of 24 and I get 1.3802. I always like to take out 3 or 4 decimals because these are very sensitive. If I round to the 10th and then I try to like take 10 to the 1.3, it's not going to be very close to 24. Next one, log of 750, 2.8751. All right, this one just says estimate the value. Okay. So I guess it wants us to just kind of do it by hand. 10 to what power equals 90. So if I had to estimate, I'd say it's a little bit less than 2 because 10 squared is 100. So I'm going to say 1.9 is my estimate. And then I can just type in log of 90 on my calculator, and I will get more accurate. It's 1.9542. Okay. So this is more accurate. All right. Base 10, because the 10 is, there's no base written. 10 to what power equals 1005. Well, 10 to the third is 1,000, so I'm going to say like 3.01 is my guess. And then I type it in log of 1005 and 3.0022. Log of 9 is 10 to what power equals 9. 10 to the first is 10, so a little bit less than 1. So my guess is, I don't know, 0.9. And I type it in my calculator. Log of 9 is 0.9542. Okay. All right. So lesson synthesis. When playing the game, how do you know if the value of the expression is positive, negative, or 0? So positive, negative, or 0. So negative would be if it was like a fraction that was less than 1. Okay. Positive would be, I guess, if it was, assuming that your base was a number greater than 1. So I guess, well, let's just say negative was reciprocal. If it was a reciprocal. Okay, so if you flipped it, if your exponent was 0 was when it was equal to 1, and positive was if your value is, I guess, not a reciprocal. All right. So like when I say positive, let me go back. So, here, this 5 to what power equals 30? Well, I know I need to get bigger. So my exponent is going to be positive. If I needed to go in the other direction, I would need to make that negative to flip it to make a reciprocal. So, all right. So when the solution to an exponential equation is estimated with the calculator or a log table and not written in log notation, how would you know if it's reasonable? For example, is 2.675 a reasonable solution to 2 to the y equals 18 or log base 2 of 18? Well, you could plug it in 2 to the 2.675 and see if it gets you close to 18. So 2 to the 2.675, that gives me 6.386, and I rounded it there, but clearly this is not reasonable, okay? So it's not equal to 18, so I would say not reasonable for this one. All right, so I can use known values of logarithms to estimate the value of other logarithms. I can use technology to determine the value of a logarithm. All right, so express the solution to each equation as a logarithm, then find the approximate value of the solution using a calculator. Okay, so this is going to be log base 10, I won't write the 10, of 32 equals p. So this is exact. And then when I just type in log of 32 on my calculator, I get 1.5051. All right, so this one here is going to be log base 10, don't write it, of 1/4 equals the exponent. Okay, so that's exact. These are exact here. And then if I want to get an estimate, since it's a base 10, I can just type into my calculator log base 10 of 1/4, and I get negative 0.6021. Okay. And again, I knew that like 10 to the p equals 1/4. I knew I had to have a reciprocal here. I knew this had to be negative because if I have a positive power, the 10 is going to keep getting bigger and bigger and bigger. So I need to get smaller to get to 1/4. So it's got to be a reciprocal. It's got to be a negative exponent there to flip the 10. So that's how I got that. All right. Well, that's about it for today. And I hope you enjoyed this video. And thanks for watching. We'll see you next time.